All right, moving on to section 3, which is on piecewise functions. You might have graphed piecewise functions before. You definitely graphed one in the activity we did in class on Desmos last lesson, right? So if you look at Isabel, Cody, and Brandon here, these are all examples of piecewise functions. It's a function that's a combination of one or more functions. So let's go ahead and state that on here, and then we'll graph a few examples. A function that is a combination of one or more functions. It's where you have a different equation for different parts of the domain. For different parts of the domain. Okay, so that example I just showed you on Desmos, the egg example, at different times when you're pulling the eggs from the carton, there's a different amount. So there's going to be a different function that represents each of those. Another example we could use, doesn't really relate today, but movie ticket prices that vary in price for different age groups, right? So you might remember when you were a kid that, say, you were, well, let's call this age, and we'll call this ticket price, okay? Our X and our Y. Where say you were between the ages, you were up to the age of 12. Well, if you were 12 and under, maybe a movie ticket was only, say, $10, okay? But then you were above 12 and you're just, I guess, an adult, not really. You got charged something more like, say, $18, okay? And then maybe a senior citizen discount, 55 and up, you were only charged, say, $12, okay? Well, what this would look like on our graph is 3 separate functions where we have age and price. You can imagine this as y equals 10, y equals 18, y equals 12, but for different parts of the domain. So for age being 12 years old and under, that's when x is everything less than 13 or greater than 0, right? If you're 12 years old and 11 months, you're still 12 years old, so you still get charged that $10 price. Then everything less than 55 years old and greater than or equal to 13 years old is that standard, I guess, adult price. And then everything greater than or equal to 55 years old is that senior discount. Okay, what's this going to look like on a graph? Well, let's label our axes here. For age, let's just maybe go by 5s. So 10, 20, 30, 40, and 50. And then for our y-axis, I'm going to get all the way up to 20, so I'm going to go by 2s. So this is 4, this is 8, this is 12, 16, and 20. All right, so all the way up to 13 years old, the price is going to be $10. So 10 is right here. 13 is, if this is 15, 13 is about right here. So I'm going to go up to 13, put an open circle, because 13 is not included. We'll put an open circle here because technically you're never 0 years old, and connect the two, showing that the movie price is $10. Then it jumps up to 18, right? So 18 is right here. When you are from 13 to 54 years old, so here's 55, we'll go right before 54, and 54, we'll do 55 and put an open circle. That way it's everything less than 55, so 54 is included in this. And then up here, we're going to put a closed circle because if you're 13 years old, that's included in the $18 price. Connect this function here. And then we'll come all the way down here to 55, not at $10, but at $12. Put a closed circle and everything greater than that. Okay, so this kind of looks similar to that egg problem that you saw in Desmos. The equation for a piecewise is going to look like this. F of x equals, we're going to open our brackets up, and we're going to have three different function equations here. So f of x equals 10, f of x equals 18, and f of x equals 12. And then you need to state the domain restrictions. So if x is less than 13, greater than 0. If x is less than 55, greater than or equal to 13. If x is greater than or equal to 55. And that equation right there represents the above graph. This specific example right here, this is a step function. It's where every single function in your piecewise function is a constant. That's why it looks like there's steps up and down the graph. So it's a piecewise function. That is constant for each interval of its domain. It's a type of piecewise function where every single function in there is a constant. It's a horizontal line, so therefore it looks like a step or multiple steps. Okay, we're going to try something a little different here where we're going to graph functions that aren't all constants. So if you look at number 1 here, we have a piecewise consisting of a linear function and a quadratic, right, for different parts of your domain. And there's really two methods that you can do here. I'll show you both. The two methods for graphing would be to use a table with domain restrictions. Probably the easiest one, so we'll start with that one first. And then the second would just be to graph both functions and then erase the invalid domain. Erase what's not true given the domain restrictions. Erase invalid domain. Okay, but let's do the first one here. So we're going to make two tables because we have two functions in this piecewise. We have our linear function and we have our quadratic. Okay, and we need to start with 2 on both because 2 is the point where this function changes. So we're going to have 2 in both of these graphs. On the linear function, we're going to have 2 and then pick another point that's less than 2. So you could use 1 or you could use 0. It doesn't matter here. For the quadratic, you need points that are greater than 2. So you could use 3 or 4. Again, doesn't matter here. I would say as many points as you need to see the parabola on there. And then we're just going to plug them in. Plug in 1 and 2 everywhere you see x. So 3 times 1 plus 4 is 7. 3 times 2 plus 4 is 10. So we're going to graph 1, 7. 2, 10. Way up there off our graph, so I'm just going to hold on that for now. Well, we actually want that on there, so let's just do this really quick. We'll move this out of the way. We'll move this down here. We'll go graph 2, 10. 1, 2, 7, 8, 9, 10. There we go. Okay. And because that's less than 2, we need an open circle. It's less than 2. All right, we're plugging in 2 now to our quadratic. So 2 squared gets us 4 minus 3, which is 1. How about for our 3? That gets us 9 minus 3, which is 6. And then 4 gets us 16 minus 3, which is 13. Okay. All right, we're going to go graph these points. 2, 1, we can put a closed circle here because that's included on this quadratic. 3, 6. And then 413 we can leave off our graph for now, and then we're going to sketch the shape. We know that this first function was linear. Okay, we can only have this line going this direction. We can't have anything to the right of 2 because it's everything less than 2. And then we know this is a quadratic, so it should just be kind of curving up pretty steep. It should not be a straight line. You know that's a quadratic. And there's your piecewise. Let's try another. Let's try number 3. It has 3 functions, and then you can finish up with 2 and 4 on your own. And then we'll do the last example, the word problem together, okay? For number 3, 3 functions make 3 tables. 1, oops, 2, and 3, okay? We need -3 for this first one, and we need some points that are less than -3. So -3, -4, great, 2 points. For our next function, we definitely want to use -3 and 1, and then pick some point in the middle. 0 is probably the easiest one. And then we'll start with 1 and another point greater than 1, so 2 is fine. If you need more to see the full shape of the quadratic, then go ahead and do that. Okay, we're plugging in our -4 right here. So we get -12 plus 8, which is -4. We get -9 plus 8, which is -1. -4, -4. Then at -3, -1, close circle because it's less than or equal to. Okay, and this is a linear function, so we have that looking just like this. All right, -3, we're plugging into this function, so this gets us 6, 0, and -2. So -3, 1, 2, 3, 4, 5, 6 with an open circle, not included. 0, 0, and then 1, -2. And this is also an open circle. Notice the 2 less than signs. We can connect these two. And then our last quadratic, plug in the 1 for x squared minus 3. So we get 1 minus 3, -2, and 4 minus 3, which is 1. So 1, -2. Okay, if this is an overlapping point, that's fine. That's going to make this a closed circle. And then 2, 1. You know this is a quadratic, so make sure it's curving up. There's your piecewise. Okay, 2 and 4 on your own. Go ahead and give them both a try. For number 2, you should have had a quadratic that was starting here at 1 with an open circle. And then the next point I would have used was -1, which would have gotten you 4. And you know this is a quadratic curving up. Looks good. Your linear function, starting at -2, it's included because it's greater than or equal to. You could just use your slope if you want, up 5 over 1. Okay, or you could have made a table. Either way. Just like that. Very nice. Number 4. Let me show you that method I was talking about where you erase the domain. So we'll graph this function, -x minus 2. So we start down here at -2 with a slope of down 1 over 1. Okay, and you could just graph the whole function if you want. Whoops. Oh, come on. Okay, and then 2 to the power of x minus 4. It's a exponential, so you probably need your table. -1, 0, 1, and 2. So -1 gets you, and again, you're down here at -4. You're really your new y-axis. It's your horizontal asymptote. So -1 gets you 1/2. Remember, just graphing the parent function. 0 gets you 1, 1 gets you 2, and 2 gets you 4. So we have something like this. 1, 2, and then 2, 4. Okay. Okay, now clearly you have some overlapping parts here. What you can do next is you can just go find 1, which is your part that tells you what functions belong where, and then erase what's left. So I'll erase this asymptote. Let's erase the linear function that has parts to the right of it because it's everything less than or equal to 1. So we're going to erase this and then just put our open circle right there and redraw that graph. Let's fix that a little bit better. Looks good. And then for your quadratic, same thing. We can erase these points, and it starts right here with an open circle curving up. Okay. I don't know. I think that's a little bit more work. It's just easier to plot points starting with where your domain restrictions are. But if you want to try that method, feel free to do that. All right. The last thing I want to finish with is a word problem. You'll have a couple word problems on the homework. This one's a piecewise function consisting of 3 different parts. So if you're running a 100-mile triathlon and you're swimming the first 2 miles in an hour, then you're biking the next 80 miles in 4 hours, and then running the next 18 miles in 3 hours. So you're going to have 3 separate linear functions. Distance as a function of time equals. Hopefully the first part's easy for us to see on here. All right, it's just 2 per every t. Let's not use t. Let's use h for hours. 2 per every hour, and that's if hours, and that's in 1 hour. So it's if your hours are less than or equal to 1, greater than or equal to 0. You're going at a rate of 2 per every hour. Okay, your next rate is 80 miles in 4 hours, which is a rate of 20 miles per every 1 hour. Okay, for our 20 miles per every 1 hour, we're going to write that in our equation, but we just have to be careful here because it's 20 miles per hour after 1 hour. So instead of putting 20h, because 20h would assume that you're starting from 0 again, we put 20 times h minus 1. Okay, 20 times h minus 1. And then you've already run 2 miles. So you add on your plus 2 at the end because that's how far we've already gone. 2 miles in our first hour. And this is if hours are less than or equal to, that was in 4, so less than or equal to 5, and greater than 1. And then we have one last function here. We now have a rate of 18 miles in 3 hours when we're running, which is 6 miles per hour. So we're going to have 6. And again, it's just not 6h. It's 6 times h minus, well, we've already been running for 5 hours now. So h minus 5, this is every hour after 5. And then we've already run 82 miles, right? We ran 80 miles here. We ran 2 miles here. So plus 82 is your starting point, and that's if your hours are greater than 5, less than or equal to 8, a total of 8 hours. Okay, I'm just going to move this function over. We'll have plenty of practice writing these functions in class and on the homework. Let's go ahead and graph this. It should be 3 separate lines. So hours down here, distance depends on time, and then let's see, we'll go every 1 hour on our x-axis. We only need to go to 8, and then for distance we get up to 100, so we'll go 10 miles. 20, 40, 60, 80, 100. Okay, and you'll really see why these equations in here, why these look a little different from linear functions that you've graphed before when we graph them on our table here. Okay, so our first line would be up to 1, only 2 miles, which is fine. So 2 miles is like barely right here. We're going to put a closed circle, and draw our line to 2. All right, then after 5 hours, here's our 5, we've ran collectively a total of 80 and 2. So we got to go all the way up here to 82, which is maybe right here. 5 and 82. We'll put our closed circle and connect all the way up here. Again, these are going to be overlapping because you're running, there's never a break in the time for this triathlon. Okay, hopefully you can see right here, this is why you need the h minus 1 plus 2, right? This function right here, it's not crossing at 0 if you extended it. It's actually crossing down here at negative something. So by having that h minus 1 plus 2, it accounts for that having already run 2 miles in 1 hour. And then finally, we're going to finish at 100 miles in 8 hours, and you can connect right here, and you have your function. Okay. If you multiply this out, 6h minus 5 plus 82, you can see you have 6h plus 52, and that's kind of where you're crossing. If you extend this line, you're kind of crossing over here at 52. I know I'm not exact. That's okay. But you can see that right there. Oh, I'm not exact probably because this point is at 7, not over at 8. Sorry, get it over at 8. There we go. And now you would probably have this more crossing at positive 52. Yep, somewhere right through there. Okay. That's why you need your h minus 5 and then your plus 82. You're starting after 82 miles for a rate of 6 miles per hour. Okay, we'll have more word problems to practice on the homework and in class together. Good luck.